The area bounded by the Koch curve, snowflake, and anti-snowflake can be easily found using the idea of self-similarity. Here's how. Let us begin by constructing a Koch curve from an initial segment of length 1. Here we use the first 5 iterations to approximate the limit fractal curve. What is the area of the region contained between the Koch curve and the initial segment? Helge von Koch, in his 1904 paper that described the construction of the curve, computed the area using a geometric series. We will use a different method by exploiting the self-similarity of the fractal curve. Denote the area of the region by the letter A. The region contains an equilateral triangle of side length 1/3, and its area is the square root of 3 divided by 36. The region outside the triangle consists of 4 self-similar copies of the Koch curve, each scaled by a factor of 1/3. Since each copy is scaled by 1/3, the area of each copy is 1/9 of the entire bounded area. These 5 areas make up the entire region, so their sum is the total area A. And this equation can be solved for A. The area bounded by the Koch curve with an initial segment of length 1 is therefore the square root of 3 divided by 20. More generally, if the initial segment is scaled by a factor of s, then the bounded area is scaled by a factor of s squared. We can now use this result to find the areas of the Koch snowflake and the Koch anti-snowflake. The Koch snowflake is constructed from an equilateral triangle of side length s by adding 3 Koch curves to the outside of the triangle. We want to find the area of the region contained inside the snowflake. The area of the equilateral triangle is the square root of 3 divided by 4 times s squared. As we just saw, the region bounded by each Koch curve and the side of the triangle has area root 3 divided by 20 times s squared. These 4 regions comprise the entire snowflake, so the total area A is the sum of these 4 individual areas. If T is the area of the equilateral triangle, then we can also express the area of the snowflake in terms of T by first writing s squared in terms of T, and then substituting this into the expression for A. This shows that the area of the snowflake is 1.6 times the area of the initial equilateral triangle. The Koch anti-snowflake is also constructed from an equilateral triangle of side length s, but now by drawing the 3 Koch curves inside the triangle rather than outside. We want to find the area of the region contained inside the anti-snowflake. The area of the equilateral triangle is the square root of 3 divided by 4 times s squared. As with the snowflake, the area bounded by each Koch curve and the side of the triangle is root 3 divided by 20 times s squared. To get the area of the anti-snowflake, this time we must subtract the areas bounded by the Koch curve from the area of the triangle. If T is again the area of the equilateral triangle, then we can also express the area of the anti-snowflake in terms of T as we did with the snowflake. This shows that the area of the anti-snowflake is 2/5 of the area of the initial equilateral triangle. So, that is how to find the area of these 3 bounded regions by using the self-similarity of the Koch curve. And as a bonus, we see that the region inside the Koch anti-snowflake is exactly twice the area bounded by the Koch curve, and the area of the Koch snowflake is exactly 8 times the area bounded by the Koch curve.